The two rows of elements at the bottom of the periodic table constitute the F block elements. These include the 14 elements from cerium to lutetium, called the lanthanoids, and the 14 elements from thorium to lawrencium, called the actinoids. While lanthanoids are characterized by the filling up of the anti-penultimate 4F energy level, actinoids are characterized by the filling up of 5F energy level. These two series of elements are, therefore, called the inner transition elements. Since the D block element, lanthanum, closely resembles the lanthanoids, it is usually included in any discussion of lanthanoids. Similar is the inclusion of the D block element, actinium, in the study of actinoids. Since lanthanoids effectively have only one stable oxidation state, +3, they resemble each other more closely than do a horizontal row of the transition elements. The chemistry of actinoids, on the other hand, is complicated. The complication is partly due to the occurrence of a wide range of oxidation states, and partly due to their radioactive properties. Now let us first take up the lanthanoids. The electronic configuration of the lanthanoids is shown in the table. Lanthanum, the D block element preceding this series, has the electronic configuration of xenon core 5D1 6s2. We might expect that the 14 elements from cerium to lutetium would be formed by adding 1, 2, 3, up to 14 electrons to the 4F level. However, it is energetically favorable to move the single 5D electron to the 4F level. For most of the elements, except cerium, gadolinium, and lutetium. The reason why gadolinium has a 5D1 arrangement is that this leaves a half-filled 4F subshell, which gives greater stability. Lutetium has a 5D1 arrangement because the F subshell is already full. The lanthanoids are characterized by the uniform +3 oxidation state shown by all the metals. Next, we look at the atomic and ionic radii of these elements. The atomic and ionic radii are shown in the table here. You can see that the atomic radii exhibit a smooth trend across the series, with the exception of the element europium. Europium, because of its crystal structure, has abnormal atomic radius. The ionic radii of the trivalent lanthanoid ions, in contrast, exhibit a smooth decrease. In lanthanoids and their trivalent ions, the effective nuclear charge experienced by the outer electrons increases with an increase in the atomic number due to the poor shielding of the F electrons. Hence, a regular decrease in the atomic radius is observed with an increase in the atomic number. This steady decrease in size of the atom or an ion among the lanthanoids is known as lanthanoid contraction. Because of lanthanoid contraction, the sizes of the third row of the transition elements are very similar to those of the second row. Thus, the second and third rows of the transition elements resemble each other more closely than do the first and second rows. Thus, pairs of elements such as zirconium and hafnium, niobium and tantalum, and molybdenum and tungsten are almost identical in size. The close similarity of properties in such a pair makes chemical separation very difficult. Now, let us look at the oxidation states of these elements. The sum of the first 3 ionization energies for each element is given in the table. The values are low. Thus, the oxidation state of +3 is ionic, and the trivalent lanthanoid ion dominates the chemistry of these elements. The divalent and tetravalent lanthanoid ions that do occur are always less stable than trivalent lanthanoid ions. The oxidation numbers of +2 and +4 do occur, particularly when they lead to a noble gas configuration, a half-filled F subshell, a completely filled F subshell. An example of the first case is the cerium-4+ ion. Although cerium-4+ is favored by its noble gas configuration, it is a strong oxidizing agent, which is evident by the standard reduction potential value of the cerium +4, cerium +3 couple. Therefore, it reverts to the stable +3 oxidation state. In addition to cerium, neodymium, promethium, terbium and dysprosium also exhibit +4 oxidation state in their oxides. The best examples of the second case are europium +2 and terbium 4+. However, europium +2, being a strong reducing agent, changes to +3 oxidation state. Samarium, like europium, also exhibits both +2 and +3 oxidation states. Terbium +4, on the other hand, acts as an oxidant and gets itself reduced to +3 state. Terbium 2+ stand as an example of the third case. Terbium 2+ ion acts as a reducing agent and changes to +3 state.